I was talking to my friend a little while ago, and he had been called in to help out build a company's 5th iteration of its flagship software platform. And I was like, 5th time's the charm, right? What happened to the first 4? Why are we doing it 5 times? And he said, yeah, it gets even more interesting. Like, it's quite a big platform. It does a lot of different things. The requirements lend themselves to microservices. But we're not allowed to do microservices. We're having to build this enormous, enormous monolith. So then we got into why microservices had been banned. And this had come about because the 4th platform had had some severe problems. The team had realized that microservices were going to help them out in this way. So they'd gone about slicing up the existing monolith into these individual services. Great. And they'd built these services pretty well. Like, they were pretty sophisticated and well-accomplished application developers. And then they'd got about halfway through the money, halfway through the time, and then they were like, well, how are we going to nail all this together? And that's when the problems started. And they started to think about the concerns they didn't know a huge amount about, that was not in their experience. And then, long story short, lots of overspend, lots of overtime later, and the project got canned because they had left the bit they didn't understand, the hard part, or the part that was hard for them, until very late in the project. And this was fascinating to me because there were lots of really good people on that project that he spoke very well of, but it just hadn't all come together. And this sort of story fascinates me. Like, how humans with good intentions come together and build software that doesn't ultimately end up doing the right thing. So we're going to see some more of these stories throughout this talk. So first of all, who am I to be talking about this? I am Fahran Wallace. I am a senior consultant at a company called Open Credo. We're based in London. We do consultancy based around native cloud infrastructure and data engineering. I am heading off happily down the data engineering track. And lots of the stories in this talk are from around my experience doing these bits and bobs. So that's who I am. I'm really curious as to who you all are for this talk. So could you give me a little sort of hand wave raise if you code on a day-to-day basis? That's kind of the day job. Sweet, okay. More architecture-y design stuff? I do a bit of that. Okay, yep. People who are more in management, more sort of strategy-based. Heyo. Good to see you as well. All right. The one that scares me slightly, any psychologists? People with latent degrees in psychology, neuroscience, that sort of stuff? Yes. I have a special favor to ask of people with these qualifications. This is not my background. I just have a layperson's interest in this, and I've read some books, and I've seen some things, and I've gone, oh my goodness, the books explain the things. But if I actively lie at any point or misrepresent the world of psychology, please be like, hey, tell me what I'm saying wrong, because I don't want to mislead, but it is not the depth of my experience. My experience is in software. So where am I going? We are going to head happily off into the world of cognitive biases, the quirks of the brain and why it is biased. Then we're going to do some examples from the world of software development, things that you can see around your delivery world that may be indicative of cognitive bias, and then some tips and tricks on how to avoid those and maybe spot that you're going to fall into a heffalump trap before you do. So what is a cognitive bias? Well, it's simply put a systematic error in your brain's reasoning. And that doesn't sound ideal, right? Why would we have those? And the reason we do is because the brain cannot be perfect. There is just too much going on in the world for the brain to evaluate all the information that's being flung at it from all angles all of the time. So we've got limitations of capacity, right? We've got about a litre of brain altogether. It's got finite memory, it's got finite clock speed, for want of a better word. We're working with, I don't know, what probably is arguably the most powerful parallel processing unit in the world, in the universe, maybe. And we've all got one. but it's still of finite size. Another reason, the second reason, is evolutionary. Thinking of all the different incarnations of animals and creatures that came towards us, we weren't really designed to be doing a lot of detailed thinking a lot of the time. We've got a lot of stuff lying around from when we were being chased by lions. These guys. We've got a lot of evolutionary baggage knocking around. So we're really, really good at spotting lions and running away from them, but perhaps, I don't know, we've spent less of our time, evolutionarily speaking, thinking slowly about things. And another reason that we make mistakes sometimes, when stress happens, when we get overloaded, we start being more reactive in our thought processes. So we're going to start at the hardware level, because I felt it was going to be a slight fraud if I didn't have a picture of a brain in the talk with brain in the title. It's a very, very basic brain model. It is more just some bits of the brain and their responsibilities slightly. So we've got the brain stem down here. This is a super old bit of the brain. It's been around for 500 million years or so. Pretty much all animals and various creatures have it. It's responsible for all the automatic stuff that keeps us alive. So it keeps our heart beating, our lungs breathing, keeps you, I don't know, when you touch something hot, you pull your hand away, your brainstem is helping you out in a super, super fast way. The limbic system is also called the paleo-mammalian cortex, hence why there's a little picture of a moose there. And it's where, amongst other things, your emotional center is housed, where lots of your motivation functions tend to be located, and animals rely on it a fairly large amounts. The neocortex is kind of like the wiggly stuff around the top of your brain. When you think of a standard picture of a brain, that's all that stuff. And it's massively connected, very complexly connected tissue. And we don't have the most of it. There is a type of dolphin, I think, called a pilot whale that has an even bigger one than us, but it's where our logical thought resides. It does other stuff as well. It's responsible for choosing what movements you're going to make, and a whole lot of other stuff. But it's where sort of your deep thinking approximately resides. So this is a part where psychologists are going to go, oh, where are we going here? But this bit of the brain is very, very reactive and fast. This one also will give you very, very fast responses. The neocortex is also super fast. It does lots of things incredibly fast as well, but it is also where the slower, more thought-out part of your thought process resides. And the people who've read a particular book will notice this language I am using and are going, aha, she's going to jump to a higher level of abstraction that she has taken from someone else. So the place where we're going now is to a wonderful abstraction about how thought works that I read a couple of years ago now, called Thinking Fast and Slow, which is a book by Daniel Kahneman, who won a Nobel Prize in economics for working out that humans aren't as perfect as economic models tend to describe them as. And he posited that a lot of the way in which we think and the flaws in how we think can be modeled by splitting the brain's processes into two different types, the fast type and the slow type. So what do I mean by fast and slow? So 1 + 1. Your brain just says 2, right? You can't stop it, it just happens. Reading var x = 2, again, if you are programming oriented, you can't prevent yourself from understanding that. Using a familiar keyboard shortcut, you've done that so many times that your fingers know it, your brain, your conscious brain may not even know it. and then recalling feelings about a particular technology. So this is sort of where it gets interesting, right? If I say, hey, let's go and write a new project together, and I want to build it in PHP, I don't know. If I say PHP, some of you will experience a particular emotion around that language. For some of you, it may be positive, for others, not so positive, but it will come to mind unbidden if you have a feeling about a particular technology. So that's sort of in the fast section. Over on the slow side, you've got to think a little bit more. So tracking down a gnarly bug, like you don't understand what's going on, you've got to think of a mental model of what is going on and then step through it. It's a slow process, it doesn't just come to you. What isolation level does the database need? Normally it doesn't just pop to you, you've got to think through the consequences. And then drawing the architecture of a system, it will take a little bit of work and you'll have to sort of think through it. So when I drew the speech bubble of that last point, I was filled with hubris. And so I got a little bit excited and I decided to try drawing an architecture diagram of Daniel Kahneman's abstraction of how the brain works. So in this little section, I'm going to start using the language he uses in the book because that's a pretty, I don't know, useful and easy thing to. So if you guys want to look this up later, you will have learned the language he uses. So the fast system of the brain he calls system 1, and then the slow system he calls system 2. All right, so let's start off. We've got your brain and body, and the world divided with a line between them, and we interpret the world using our senses. That seems fairly okay, and we'll put system 1 into the fray. System 1 is able to make pretty fast snap judgments about the world. It's monitoring the senses. So if you hear a woof and see something fluffy with a wet nose, and you'll be like, it's my friend's dog, and you'll immediately think, happy, yes, maybe I'll go pet the dog. So system 1 is offering all of these abstractions of the world. And system 2 is there too. You're able to sort of sit with your conscious self and look at all of the abstractions and all of the information that system 1 is sort of bubbling up for you. And you can choose to intervene if you want. You can choose to, I don't know, walk this way, walk that way. Or you can let system 1 do the automatic thing it is just going to do anyway. So I guess the other interface with the world is our actions. We can do things. So for example, system 1 might do an automatic action. You might see a lion with your eyes. The lion recognizing part of your brain will light up fairly rapidly, one would think. And you might automatically be filled with the urge to run away, and then system 2 is like, yep, not going to argue with that diagnosis, off you go. So system 2 can interface with system 1 in other ways. And at this stage, I sort of started thinking in more the languages of a cache. It felt like system 1 was responding pretty immediately. And you could sort of ask the main back-end system for more information, but the cache was doing pretty all right with sort of default responses. So for example, if you're fed up of running away from lions and you want to learn to fight back a bit, you can put some effort into learning a new skill. You could take up the bow and arrow, you can practice really hard, you can build into your muscle memory how to draw a bow, and then perhaps you can train system 1 to think, now you have 2 options. Now I can run away or I can fight back. And so the interface between system 1 and system 2 is a discussion that goes all through the Thinking Fast and Slow book. But Daniel Kahneman posits that where the interface between these 2 systems is a little bit imperfect, you get interesting things. So system 1 is constantly providing information and suggesting actions. These actions are reactive, immediate, and crucially, simplifications of reality. There's not much nuance in system one. It's very much see lion, run away, see PHP, maybe run away, I don't know. System 2 uses those approximations to inform its slower and more reasoned process. So system 2 is like, can calmly just sit back and watch. But when system 2 forgets, it's recalling simplifications and seeing simplifications from system 1. We can experience cognitive biases. So the question becomes, are we logical? Do we think that system 1 is broadly in charge of our actions? Or do we think that the more logical, slower, and more reasoned system 2 is calling the shots? Professor Kahneman, I don't know, posits that system 1 is more in charge than we would like to think. And I am inclined to agree with him. So, cognitive biases. This is not a chart made by me. It was created. The categorization was done by a guy called Buster Benson, and there's an algorithm designed by John, I can't read it, Manoogian. If you Google for this, you will find it, and it's a wonderful little synopsis of a lot of cognitive biases. You can't read it from this room because it's too small, but it's mainly here to show you just the range of the problem. These are all the uniquely identified problems that the brain can have. We're going to go through some of these examples in a bit, but the categorization that was done sort of grouped them loosely together, and I found this quite an intuitive grouping, so I've sort of taken those groupings and used them for this. So the 4 groups of cognitive bias I want to talk about are ones where there's too much information coming at us too fast, and we have to filter some of that out. There's not enough meaning, so we're filling in the gaps from our experience and other places. The need to act fast, so we've got to make a snap choice. What informs that choice? And then how do we remember what we did? So let's go through some biases that we've seen. Too much information. All right, let's try something. I did this once before. I like to think it worked, but let's have a sample size of 2. All right, pick a number, any number. Just think of it in your head. No, just kidding. Now pick another number, this time a number less than 5 million. All right, so what I'm trying to do there is, let's see, whose second number was larger than their first number? I didn't do it, I'm lying. Okay, it's hard to say whether it's statistically significant or not. But the general gist of it is, there is something called the anchoring effect, which means that when you're asked to make a sort of impartial choice between things, you're quite likely to anchor that choice to bits of information. And the bits of information you anchor them to can be totally irrelevant, but nevertheless can sort of make you more pinned towards that. So, for example, when you're doing an architecture diagram, when you're scoping out a system for the first time, let's say you're choosing a database, there's a lot of different choices available to you. But you are quite likely to not deviate from the first one you pick. So you'll start drawing and you'll casually write down, oh yeah, DynamoDB, because the other database like this is DynamoDB, and then move on. And then, on occasion, it turns out DynamoDB does not have the correct requirements for that system. But you're not quite inclined enough to move away from it. It will be your favorite. Other things in this nature are available too. So there's a thing called the availability heuristic, which means that things that are more available in that fast system 1 cache, that are hotter in that cache, will come to mind more. So things that you've used recently, and there's no harm in prioritizing tools that you and your team are familiar with, but just as long as they're suitable for that problem. So to summarize what you do in the face of too much information, you rely more on your cache, that fast system 1. And that cache is a simplification of reality. Your initial thoughts are harder to evict. And hot items in that cache, even if they're hot from an entirely different context, just because you have used that database recently or used that technology recently, have higher priority in that cache. So it means that you might just gravitate towards them a little more. So what can we do about that? So thinking back to times where clients have been super enthusiastic about getting to the point of building the system they want to solve their problem. There have been times when they've been super excited to start drawing out very, very specific pieces of infrastructure. So they were using the Amazon cloud at this point, so they were happily being like, okay, we need a message bus. We need, let's use Kinesis for that. And then very, very rapidly, a very specific architecture that probably satisfied most of the requirements got put on the whiteboard. But when you dug into the detail of it, you found that perhaps things weren't quite the right shape. So we started using this super handy tool. It's a thing called C4 diagrams, and it's written about in Simon Brown's Software Architecture for Developers book. And it is a super useful framework for just slowing things down a bit, keeping the architecture just a little bit more abstract and requirements focused rather than specific and I'm going to use DynamoDB even though I haven't quite worked out what the requirements around my database are. So how it works is you start out with the system context. You basically draw a box containing everything that you would build, and you draw all your dependencies around that box and the interface points between. Then once you understand your external dependencies, you break it down into containers that have broad requirements on them, but still no specific technologies yet. And then now, once you've drawn those two diagrams and you've understood the context behind the system, you can start drawing your components and getting into specific technologies. Once you understand you kind of force yourself to slow down until you get to that point, and then you learn a lot on this journey down here. So the need to act fast is our next set of cognitive biases. So there's a lot going on. You've got to deliver. You've got to get something out the door. You can see a deadline in the future, and you're not quite sure how you're going to get there. So let's start building. But remember that project in the first little bit of my talk. The microservices platform that had died because they hadn't thought about how to integrate the microservices together, which is, it turns out, quite a hard problem that needs a lot of careful thought. This is something called the hard-easy effect. So humans are super inclined to do the easy stuff first because we want to, when we're faced with lots of work, we want to feel like we've got some stuff done. And we feel like we've got some stuff done when we've built something. And that's, I don't know, it gets us going, right? It gets us starting out on the journey. But you start climbing the wall, and then halfway up the wall, you're a bit like, I wish I'd looked a bit higher up the wall and seen how to do the awkward bit before I got there. And it's one of the pitfalls that I see quite often with people doing agile delivery. Right? Agile says, just do the work you see before you and finish that and then look and do the next bit. And that's a great idea for keeping delivery fluid. But if you're leaving out the end-to-end of this, if you're iterating and doing all the agile parts of this part of your delivery, but you're leaving the hard part that you don't know a huge amount about down here, you may well have a bad time. So this little matrix can help, or at least the copy in your brain maybe. Do the hard stuff first. Do the high difficulty, high value stuff. Get something working end to end, even if you don't understand a good chunk of it. Go and understand how you will do that, and then get it done. Then the rest of the stuff kind of falls out. Do the high value, low difficulty stuff second, because there will be no surprises if you've done the hard stuff first. Fine, do this third. Don't bother with hard, low value stuff. But lots of projects don't do this. Lots of projects run happily towards the high value, easy stuff, and then forget about the hard stuff. So this is a paper that has now become pretty famous. Back in the 90s, Professors Dunning and Kruger released a paper where they'd basically discovered that the more confident someone was about what they were speaking about, the less it turns out they were skillful in that area. And vice versa, the more skillful someone was in an area, the less likely they were to be confident when communicating about it. And it's quite fun to, it's quite fun to think about in the context of how you're working. This diagram is not from their paper, but I quite like how it evolves. So this sort of feels a little bit like how you experience new technology, or I do. So for example, about a few years ago, I took up the ukulele. And for a little while, everything was going okay, right? I was like, oh yeah, I can play chords, I'm a musician now, this is wonderful. Oh no, at this point, I learned enough to, my musical ear kicked in. I'd never really had one of those before. My musical ear is horribly judgmental, it turns out, and I'm a really bad ukulele player. So down we went into the pit of despair. And now, through even more hard work, you can gradually crawl out of the pit of despair and achieve mastery. But your confidence seems to be proportional to, your confidence level is very susceptible, shall we say, to unknown unknowns. You at some point become aware of what you don't know through gaining knowledge about something, and then your confidence declines enormously. And because there are so many technologies and the world of programming is so vast, I feel like we're all surfing this curve lots of the time, and a lot of us end up here for lots of different technologies, and all of us think that we can't do everything and everyone else is better at everything than us. This is a thing called the Imposter Syndrome. And almost all of the developers who I respect and have had a conversation about this with have been like, yeah, no, I know nothing. I feel like I know nothing all of the time. So I find that quite reassuring. So I guess my encouragement for this is to relax. We all feel this way. It's okay. Programming is big. And providing you're not hanging out here for everything you do, everything's probably okay. I think feeling like you don't know everything is probably healthy for us. So, we want to move fast. By all means, use that urge to get yourself going, to get yourself building something. But we're bad at assessing how much we don't know. You need to make sure that unknown unknowns aren't going to trip you up. Because System 1 isn't really aware of unknown unknowns. System 1, this fast little bit of your brain, is just reporting on what it can see and what it can experience. And System 2 has to go and inspect and go, no, actually, there's this big fuzzy blob where I have no idea what I'm going to build. So to fix this, we can do the hard stuff first to increase your rate of useful learning, and go do spikes in that area. but make sure the fuzzy blob of I don't know how I'm going to deliver that is explored at some point. So what do we remember? This is a whole fascinating area in itself. It could be a whole talk. It's not. But memory is wonderful and terrible. So the brain has finite memory, as previously discussed, right? And so it has to compress things. That's what computers do. That's what we do too. But we don't compress stuff like JPEGs. We don't just make the memory fuzzier and uniformly just a bit more vague. Our compression algorithms are quite specific. So we remember kind of like Photoshop's context-aware scaling algorithm. We remember the emotional high of a situation quite strongly, and we remember how a situation ended. So in terms of a project delivery, you might remember, oh, there was that really tough time when we were going live, and then everything ended up okay. But you miss all the detail. And even better, like your brain makes up detail that you have forgotten. I did this when I was going over this talk. The last time I gave this talk, I lied. I said, I read Thinking Fast and Slow, and it was great, and it gave me a model for understanding the world, and then I wrote a talk about it. And then I went through my notes and my diary, and I was like, no, there was a version of this talk that did not mention that. And I had just, because that book had that impact, I had then rewritten my memories around how this talk had evolved to counteract for that. Brains suck, man. I lied on stage. Oh well. So yeah, that's sort of how the content-aware scaling has happened. You remember the dolphin? The dolphin was an enormous emotional highlight. But the splash was important too, and that 2 years later, you've forgotten everything you learned about the splash. So there are tools to help with this. I really like architectural decision registers. When you're going through a project and you're hashing things out and you at some point have to make decisions and you're a bit like, I think I am doing the right thing. I'm not really sure. How do I validate that? Write down what you decided and why you decided it. Because in 2 years' time, you're going to have forgotten that detail. And you're going to be looking at the system and going, oh, why don't we were weighing up 2 technologies a couple of years ago, and we chose this one, but actually maybe this one will do. And all the context and the thinking you did earlier on will have sort of fallen out of your memory. So I love architectural decision registers, just because occasionally you find, and especially if someone else's, like a previous tech lead has written an architectural decision register, occasionally you find absolute gold dust in there. It can really help you understand the context of your project. So not enough meaning, the last of our sections. Brains like stories and patterns. They're really good at pattern matching. So for example, this is a pattern. Look at that. It's a line. Chocolate consumption per year per capita, and Nobel laureates per 10 million people. Chocolate makes you smarter. That's how it is, right? No, chocolate, I wish it did. Chocolate does not make you smarter. At least there's no evidence that supports that. It just means that Nobel laureates tend to be from vaguely affluent, vaguely European-centric countries. And so we get to laugh at this one, because the story isn't very good. Like, your brain doesn't latch on and go, I am compelled to believe chocolate makes me smarter, because I'm pretty sure would have heard about it if it was true. So confounding variables are sometimes harder to spot. So for example, there was a furore a little while ago because it was discovered that there was a correlation between ladies who are going through the menopause taking hormone replacement therapy had a greatly reduced risk of heart disease in later life. And you can sort of see where a story comes in there, right? Doctors sort of were thinking, oh goodness, there is some not understood relationship between, what's the words? The chemicals that make you feel things, man. What are they? Huh?
Neurotransmitters?
Let's go for one of these. Yes. Yeah, between let's go with neurotransmitters. I like that one. That one sounded good. And coronary health. And so loads of research sort of started heading off into looking into the causal relationship here. But it just turned out there was a confounding variable, which was wealth. It turns out that people who take hormone replacement therapy are more likely to be affluent, and people who are more affluent die of heart disease less. So that's once you understand it, you're like, oh yeah, that makes a sad sort of sense. But until it's explained, the brain loves a story. And if it's a believable story, your brain just sort of automatically thinks it's true. It goes into that cache. And then you have to consciously think about evicting it from that cache. So here's a super dangerous version of this. Stereotyping. We do this. We can't not do this. When you say, think of a French person or a British person, little templates pop into our head, unbidden, and then when you're interacting with someone who is of that description, you're filling in sort of bits from that template. So if you meet 3 people who dance and they wear red shirts, the next time you meet someone with the red shirts, you're going to be like, hey Bob, how's the dancing? Maybe not, I don't know, but it's because we're sort of filling in from these templates. There was a wonderful talk yesterday, in fact, about the encyclopedia, our sort of cultural encyclopedia of that we're filling things in from, and that made me think of this aspect. I don't have a remedy for that really, but it is unfortunately a little bit how our brains work. So cargo cults. I love the origin of the term cargo cults. I've just sort of used it, but I hadn't dug into why it was called that. It turns out that there were, in the Pacific Islands, there were people who had not made full contact with other people in the rest of the world yet. But there were lots of planes flying overhead because war was happening around there, and the planes were dropping supplies, cargo, lots of stuff that was very interesting and was really changing and enriching these guys' lives. They were receiving new foods and synthetic clothes and stuff like that. And then the war stopped and the planes went away, and the native people wanted the good stuff to come back, right? So they started building these beautiful sculptures of planes to sort of try and encourage the planes to come back to them and bring them the cool stuff again. And it's super wonderful and so human. And we do this a lot. This is always happening all of the time, I think. Even when we think, I don't know, we've learned from things like this. So, for example, Agile is quite often accused of being cargo culty. Like if we're doing a daily stand-up and we're doing our retrospective and we're having our planning sessions, we're doing Agile, right? It doesn't matter that our code is released once every 6 months. We've done the process. We have built the model plane. Why aren't the planes coming? It's not just in the sort of interface between software and the business world, though. This is a picture of how I interpret Scala in my head. Scala is a fantastic language. This is no malignment on Scala. But I once worked on a project where it was in a Java house, and Java was, I don't know, pretty well understood and I guess kind of boring to the people who were being asked to code it. and they wanted to get all the purported benefits of Scala. So functional programming is more expressive. You need to test less because the type system is so wonderful. And they'd sort of learned these facets of Scala and had heard these things about Scala, but the practice of understanding how the type system means you can have fewer tests ultimately just meant we had fewer tests, and it didn't work. So I think programmers are vulnerable to this sort of thing as well. Scala is great, don't hate me. All right, so this is my favorite name device. This is a thing called the IKEA Effect. And it just means things that you built, you love more than things that you did not build. So the janky little coffee table that you nailed together when you were leaving university is still beloved in your heart and much better than the one that has just been given to you by your landlord. It also means that your janky little testing framework that does successfully test the application, but in the 10 years since it was initially built, has now got a smaller feature set that is much less well documented than commonly available solutions. It might be time to let your little testing framework go, even though it's wonderful, even though it served you well and you love it. So another facet of this aspect, estimation of time and complexity. It gets its own section because we're really bad at it. And we know we're really bad at it, and even though we know we're bad at it, it still doesn't save us from being bad at it. But it's a hard problem. So part of this is exponential complexity. So you have a requirement, and it's sort of why waterfall tends to underestimate things unless you have planned extremely, extremely thoroughly. Because we're quite good at understanding how many things we need to do, but we're not very good at understanding how the things we need to do interrelate and how the complexities will expand the more things we try to do. So I worked on a project where it was a checkout application. And it feels fairly linear in your mind, right? You're put the thing in your basket, pay for the thing, say where you want it to be sent, do you want any other random extras, done. But it was being done on a quite short time scale. It was a rewrite of that Scala application I was talking about earlier. And the business was sort of saying, why it seems quite linear. Why is it taking you? Why is it not just done immediately? And so we sort of tried to answer that question by looking at the requirements we had. And there were lots of edge cases, lots of details. So it wouldn't be like if you're having something, if there's nothing to deliver, you don't need an address. If there is something to deliver, you've got to have a billing address, and it may or might not be the same as your delivery address, that kind of thing. And it turned out that through it being quite a complicated thing to buy, there were 70 paths through the checkout that needed to be sort of tested and looked at. And so we sort of ended up looking at the outer edge of this ballooning requirement stock. So we kind of printed out the spreadsheet and gave it to them, and then they were like, yeah, okay, I can see why us giving you these requirements sort of ad hoc has made everything be quite complicated. So we slimmed it down and made it an easier set of requirements, and everything was sort of okay. It's also why we try to estimate things using Fibonacci numbers. I hadn't twigged this before. So you know how when you're doing planning poker, you're sort of allowed numbers 1, 2, 3, and 5. And then you start having to jump and do these larger leaps. That's an effort to sort of factor in this branching complexity. The theory is that if something is a bit bigger than a 5, then it's going to intermesh with other stuff and be more complicated than you think it is. So this is trying to help you not underestimate. So thinking back to what I said about memory, I said that we remember the emotional highlights and we remember the end. This is the end. And the reason I put this one at the end is because I want you to remember this one the most, because I hate this one. It's my least favorite aspect about certainly my brain, possibly all brains. It's a thing called the Backfire Effect. And so when our brains are confronted with a new concept, totally innocent, could be a really good, amazing, fantastic idea. But there's a problem. You have already got something in that fast System 1 cache that is incompatible with that new concept. For whatever reason, it may be in there for legit reasons, it may be out of date, maybe it should have been evicted a long time ago, but it wasn't. But when something comes in and it conflicts with an existing cache entry, your brain has a really strong reaction to that. The amygdala, which is the little bean that governs your emotions that sits kind of in the middle of your limbic system, lights up, and it treats the new concept as a threat. Your heart rate typically increases a little bit. You feel a response to that new concept. You experience its impact with your cache. And then, even better, you sort of double down on this. When pushed even further, your brain like builds walls and is like, no, things in my cache are sacred. I don't want to question that. And it takes quite a lot of work by System 2, especially if it's a deeply rooted thing in that fast System 1, to evict the old entry and to evaluate the new concept and be like, actually, that's the one that should be in the cache. We need to change how we are. There's no good response to this one, really, I don't think. I think there's a wonderful cartoon here, which is by The Oatmeal. It's where I first read about the Backfire Effect, in fact. Go read that. It's fantastic. It's such a good cartoon. But it lays out precisely how the brain is responding to these threats. And it cancels letting the brain have its moment, have its response, because it's a rapid response, right? You can't prevent these things. But train System 2 to spot it and be like, wait a second, let's inspect that feeling for a second, make sure the correct concept is winning here, and then try condition yourself to have the right concept cached. But I now see this everywhere I go, especially in the current days, and I hate it. I hate that brains react this way. So let's recap not enough meaning. We should beware the stories the brain tells itself. Because if the brain successfully tells a story that makes sense internally, it will just sort of believe it. That will go into its cache. If you read a news article that it turns out that actually it's retracted a few days later, you'll still remember the first iteration of the article. You won't remember the retraction so much. Let your reaction have its moment and then reevaluate. That's all we can do in the face of our reactive little brain. And then, as a way of getting by in the programming world, present new ideas to others in ways that complement their existing views. Because you're going to have a much more happy time at work if you're trying to work with people, and if you're aware that they hold a very particular view. Setting that off is going to help no one, really. So what just happened? A quick plot summary. When the brain is faced by too much information, we use heuristics to discard some of that information. These heuristics can be accurate and they cannot be accurate. We feel the need to move fast. We feel overconfident and we focus on quick wins. We try to feel like we're going somewhere. Memory is finite. So we remember the emotional highlights. We forget the detail. Learning from the detail is important. And there's not enough meaning. The brain tells stories to provide meaning to data. and then believes them somewhat automatically. So what can we do? When there's too much information, we can engage your logical brain and break down the problem. Use those C4 diagrams if you're doing architecture, for example. Try, break down the process and understand why you're making decisions at each level. When there's not enough meaning, validate your gut instincts. Be mindful if your cache does not match reality. We need to move fast. Do the difficult stuff first. Make something work end to end, even if there's a hard part in there. And we need to remember our reasoning. Document and reflect on your decisions. Write down what you decided. Because future you will be really happy that you did sometimes. And this is the part where I sound a bit like your mum. Get enough sleep and avoid making decisions under stress, because they will be worse. Other things you can do about all of this. That is a link to the Backfire Effect cartoon, which I love. This is the book that's language is heavily used throughout the talk, and really changed how I think about how I think. Software Architecture for Developers by Simon Brown has those C4 diagrams in, and lots of other ways in which you can break down doing architecture and think more slowly about your software. And Oliver Sacks, The Man Who Mistook His Wife for a Hat, is, I think, what started me off thinking about brains in the first place. It's a really good description of lots of case studies of how brains work and don't work. That's all I got. Thanks very much for listening. Do we have time for questions?